he's always like very pleasantly smiling and happy to fix problems. So I'm always very grateful for him. And we're here today to hear him talk about DAG type schedulers for the last parallelism talk.
Thank you. Hello, everyone. So I'm going to talk about a scalable DAC scheduler we have been trying to develop. Just a brief of what a DAG is. In simple terms, it's just a bunch of computation and data put together as a graph. We can think of the edges as functions and the vertices as the data as input to them. In Julia, I guess I need to. So in Julia, we can use the nice package Daggar to create DAGs easily. So Daggar has this delayed function which lets us provide a function to execute later with some parameters. And what we get out of it is a thunk. And we can create multiple thunks and chain them together to get a DAG. So here I'm using Daggar to create a DAG which computes the square root of sum of two squares. And I'm using GraphViz to visualize it. And so this DAG is not run yet until I do a collect operation on it. That is when it goes through the graph and executes the nodes in the right sequence and gets the result. So it is quite apparent looking at this graph that a DAG helps us determine the correct order of execution. And it can also let us identify if there are any reusable units in the computation, and whether there are any blocks which have special resource needs, like GPUs or high memory instances or whatever. And with this information, a scheduler can easily parallelize and schedule each of the nodes of the computation. These are the goals that we started with to develop our scheduler. The first goal is, of course, to execute the DAG, but prioritize tasks that promote parallelizations. Now, what are those tasks? Those are typically the tasks which are used in multiple other tasks downstream. So those are the points where the data, the result is either broadcasted or distributed to other nodes. So identify those points and prioritize them. And then respect data locality, because moving data across machines is expensive, or even across processes is expensive. So try to minimize as much as possible. Optimize resource usage. So one typical example is, let's say we have computed something using a GPU, so we have been running on a GPU machine, but our next step is does not need a GPU. So should we continue running on the GPU machine, or should we move on to a CPU machine? What? So that's a resource optimization we need to decide on. And this is an example of a conflicting requirement. So if we move to a CPU machine, we need to move data, but if you continue using the GPU machine, we are holding a GPU idle. So so which one should we do? So it should allow us to tweak the requirements. And while doing all this, we want to be scalable. Typically in a large problem, if we have centralized scheduling, the scheduler can become a bottleneck. So we try to distribute the scheduling, and to become resilient, we try to put a state store and identify failed tasks and reschedule. And another problem we try to avoid with this, which is there in current Julia, is to avoid getting locked out from a busy executor. So when an executor process is computing, it cannot respond to messages from other processes which may need data from this process. So let's say one process has two results, and one of the results is needed by another process. That process will have to wait if this guy is computing. So we try to avoid getting into that problem. So how do we go about doing this? The first thing that we do is to decompose the DAG into smaller chunks. Now we decompose at those points where what we call as layers. Those are the points where the data is broadcasted or distributed, as I spoke earlier. Also, we identify points where chunks which need specific resources, or the same set of inputs, and those points are from those points our chunks are created. So once we have created coarser chunks from our DAG, we have a central scheduler which schedules those chunks, and we have scheduling at node level, which takes up finer scheduling from those chunks, from each chunk. And we minimize data movement. At the same time, we try to overload any single point. This we do by creating a stack of instructions. So as a process which is scheduling portion of the DAG is walking through the DAG trying to execute nodes, it pushes each node into a stack, and the stack has a finite threshold size. If it goes beyond that, anything else which overflows is a candidate to be which can be stolen by any other node which is looking for a task to execute. So this diagram should make it clear. So we have a central cluster level queue from where each node can pick up tasks, and there are multiple executors on each node, which each of them have their own queue, and when their queue gets when each queue gets overflown, the tasks go to a common queue which is the candidate for stealing. And we have special processes called brokers, which take care of stealing tasks back and forth from the central queue. So each node has a broker process, which is not an executor. The broker process takes care of doing this balancing of tasks between nodes and the central queue. So the broker process also takes up this task of offloading expensive I/O between processes. So if a piece of data needs to be given out to other processes, the executors hand it over to the brokers of each node, and any other node talks to the broker process to take the data out. Since the broker process is not doing any communication, is not doing any computation, it's only doing communication, it can handle multiple I/O communications at the same time. So this is a brief of the model. With this, we have got good results. And so Daggar itself has a scheduler which is quite good, and we are comparing against that. And with the sample, one sample here, we are getting good speed up, about 4 times speed up from what we get with Daggar. I'll show a small demo of this. All right, so here yeah, so I've already done the add procs here. Yeah, so I start with a single process. This is running on my laptop. I add 5 processors. And so this is a package which is not yet public because it is under development. I start using the DAC Scheduler, and the DAC Scheduler automatically plugs itself in as a scheduler in Daggar. Daggar itself has a scheduler, but if you start using DAC Scheduler, it will replace the Daggar Scheduler with itself and take over the scheduling from Daggar. That's what has happened here. And I'm using some other packages to help me visualize things. Here I'm setting some parameters for the scheduler. So we use some shared memory communication between the nodes, and I'm just increasing the capacity here. And I create something called a run env. So when I call this, DAC Scheduler goes to the process graph and figures out tries to detect how many nodes we have and makes clusters of processes of each node and then joins them together to the central process. So here it says that I have just one machine and I have two workers 2, 3, 4, 5, 6 and one is the master node. And then, so here I have generated a DAG, try to make it a large DAG. So it's something like this. It has around 4 or 5 layers. And yeah, it's pretty big. And when I run it, I'm just checking the result to be same. And I can also see that, see how the tasks got distributed. So it's not like exact uniform distribution, but you can see pretty much executor 4 got a bunch of, got most of it, 680 tasks, and the rest of them got divided almost equally between other executors. So it's likely that executor 4 is what took the first task, which is the largest tree, and then from there it shared, whatever it shared got onto other ones. And here there is another example of a DAG, which is like a complicated DAG, which is quite cross-connected. So here we have lots of those points where the data needs to be shared. So the central scheduler will be doing a lot of work here. And I'm just checking the result and checking how the tasks got distributed, which again is pretty uniform distribution. Yeah, I'm just cleaning up here after that. So that's it. I have take questions.
So do you plan to have like several schedulers available within Daggar to pick and choose from, or is this sort of a separate thing? Is it going to be only scheduled for Daggar?
So as a part of this, I have updated Daggar to accept other schedulers. This is one of the schedulers. So now there is a facility to plug in a scheduler to Daggar. Yeah.
So Tanmay, do you have a sense of how long, what is the overhead associated with a non-trivial scheduling job like the one you showed?
The overhead of scheduling?
So for example, the cross-DAG example, the one with the very complicated data dependency, like, do you have a sense of how much overhead is introduced just by having to schedule it?
I don't have a figure right now. It is significantly lower than what it was with Daggar, because a lot of the scheduling happens locally on the same node. But I don't have an exact figure.
This more being used for very long-running processes, or is this also something that could be used for more real-time critical processes like control systems or software-defined radio, where you also have a processing chain, a DAG, but you want to run through the entire DAG maybe many, many times per second?
So with what we have right now, we can only run long-running processes because we haven't yet implemented a way to run different DAGs on the same cluster. So once the cluster is up at one time, it can right now run only one DAG, and once it is over, only we can run another DAG. But with once that is available, we can run multiple DAGs, and shorter DAGs also will run quite efficiently.
Great. So I think that will be the last question, and we can take all the other questions during break. I'd like to thank all the speakers again. I think it's very brave to have a whole session where every talk had a demo. So that's something I've never seen before at JuliaCon. So thank you, everyone, who made this possible.
Thank you.